Good evening, everyone. Am I audible? Am I audible to all?
Yes, audible.
Yes, sir.
Okay, thank you. Okay. So today we will be doing the week two of this course, Computational Fluid Dynamics. I'll be conducting the live session. So uh, let's start. So in the last session, we left with classifications of second order partial differential equations, and in relation to the number of characteristics that they have. So we had these three classifications: elliptic, parabolic, and hyperbolic. Hmm. And they have their own unique set of properties based on the number of characteristics. So in elliptic is basically with no characteristic, with parabolic has one real characteristic, and hyperbolic has two real characteristics. So we let's revise a little bit. So we classified this for this particular equation. So like this can be assumed a general quasi-linear equation, but uh, for a quasi-linear things will be a little bit different. For a linear equation, it this classification is very straightforward. And how do we classify? So what we basically did was we used this equation, and also we like use two other equations which are basically so that the partial the second order uh, the first order partial differential, the phi x and phi y, they are totally differentiable. Total differential means like they can be written like this. So the phi x can be written like this. If someone is trying to join, I will uh, admit them. Yeah. So this can d phi s can be written like this, and this d phi y can be written like this. Now, what we are actually trying to find, we are trying to find characteristics, and how we have we defined this characteristics? We have defined this characteristic as the curves where this second order partial differentials may be discontinuous, right? Uh, so so for that scenario, we will need these three sets of equations to have no solution. So we did that, and we found out a particular equation, a quadratic equation of the form dy dx square minus b dy dx plus c equal to 0. And means from this only, like quadratic equation, since this is a quadratic equation, we will have three conditions, and from those three conditions we arrive at this three classifications of elliptic, parabolic, and hyperbolic. So what are these conditions? So if my b square minus 4ac, this is if this is uh, less than 0, then I will have no real characteristic. So this will become elliptic. This is elliptic. uh, b square minus 4ac. If this is equal to 0, then this is parabolic. Uh, b square minus 4ac. This is greater than 0, then this equation will have two solutions, and thus will have two real characteristics. This is hyperbolic. So this is till this we had done in our previous class, previous live session. So if anyone has any question, can please ask that regarding the previous live sessions and all the topics covered there. Okay. So proceed. So as I said that there are mm, yeah. As I said, there are different properties of this elliptic, parabolic, and hyperbolic equations, and we discussed this little bit in the last class. So one example of this elliptic equation is the Laplace equation. So Laplace equation looks like this, and there are few very like strong features of this Laplace equation. One that is it is always a boundary value problem. We specify the either the value of this phi or the first derivative of phi at the boundary and solve this equation. So this is so elliptic equations in general are likely to be boundary value problem, and they will have a domain in which we will try to solve this. We are anyway doing numerical methods, so we will have a finite domain where we solve these problems. So in that finite in that domain, the information that travels across that domain will be at an infinite speed. So any disturbance anywhere in the domain will travel to the rest of the domain at an infinite speed, which is unlike the hyperbolic equation that we will come to. Well, before that, there is a parabolic equation. Parabolic equations are they are generally the time derivative equations. These fall in this category. So if I have the conduction equation, for example, so conduction equation is a classic example of a parabolic, and so this is an initial value problem. You specify a time t is equal to some particular value. We specify an initial condition. So suppose t is equal to 0. Uh, I have some phi value. So using this, we solve the rest of the problem. So here it is an initial value problem. So at a particular instance, some value is specified, and that value um, basically influences the values for t greater than 0. So someone is trying to. Okay. All right. And what happens with the hyperbolic equation? In the hyperbolic case, this is basically the equation uh, will not propagate at infinite speed. However, this will propagate at a finite speed. And the wave equation is one of its example. If I find the so this is one dimensional wave equation. You can put some constant. So this is one dimensional wave equation. Uh, so here we have previously also discussed that the information across the space it will travel at a finite speed, which is defined by this coefficient. So that is basically the difference between these three types of equation, and our solution strategy will depend on whether these equations are elliptic, parabolic, or hyperbolic. So let's do some problems regarding these classifications, and then we will move to the next topic. Okay. So this question is there. Second order partial differential equation is given. and there are two statements. So characteristics of this equation are given by the following solution of the following quadratic equation, and whether D is required or not for finding the characteristic. So, so let's talk about the first statement. Like, is this correct? Can someone
Yes.
answer? Hmm? Is this correct? Yeah. Please, you can unmute and like let's have the discussion. Uh, can unmute and speak. Yeah, anyone can unmute their mic and speak. Uh, there is like this is meant for an interaction session, so like there should be interaction in this session.
Yes, sir. I think first is correct and second is wrong.
Second is so first is correct. So we have like we just discussed also, like there will be a quadratic equation that we come across, but is the form correct? Are you sure? We can, so we can remember the matrix that comes about. So A, B, C, and this is dx dy 0 and 0, and this is dx. So this is 0. This is the matrix that comes up. So uh, please like expand this, and if you expand this, you will get the expression. This simply simple determinant.
It has to be negative p, right?
Hmm. Okay. Yeah. So if we expand this, what we get, like a into dy into dy. So a dy square. Yeah. So a dy square. Then the second integral is d 0 to 0 and minus dx into dy. So this will be minus dx dy. That's why this minus sign is basically coming. So plus c dx into dy. This is equal to 0. So yeah, if you arrange like this equation is correct, but there will be a minus. So we will report it as wrong. We will report it as wrong. So what about the second statement? Is this correct?
Yes, it's correct.
So D is not required for finding the characteristics of equation. Yes, so we like just now found out like what we need to solve for finding the characteristics, and this is the this quadratic equation, right? So this quadratic equation is required to be solved to find the characteristics. So D is not required for the solution. So this statement is correct. So we will mark answer option B as the correct one. Only the second option is correct. So we have another problem here, and this is based on the Laplace equation. We just now saw that this is elliptic in nature. So, like this. this the operator. So this operator can be basically expanded like this. Uh, if in 2D, if in 3D, then there will be a plus z square. And so this is acting on phi. So this is basically del square phi del x to plus del square phi del y to equal to 0. And if we like find the characteristics, we will see that like, the b square minus 4ac what is coming, that is negative. So this is elliptic. So again, these three statements are given. You answer whether like these are correct or not. So these are basically they are asking about properties of elliptic equation. So the first statement is any disturbance in the domain propagates in all directions at infinite speed. Is this correct?
Yes, correct.
This is correct. Yes. Uh, any disturbance in the domain will propagate in all direction at infinite speed. This is the property of the elliptic equations. So this first statement is correct. What about the second statement? The transported variable at a point is affected by all its neighbors. So is this correct?
Yes, it's correct.
This is also correct. So basically, since there is no characteristics, so there will never occur any situation where like there is a change occurring at a point and the neighboring point are not affected. So if a change is occurring at a point, it will always affect the neighboring point in case of elliptic equations, because there it is like there is no characteristic lines which is prohibiting it from affecting the neighbor. So that's why in elliptic equations, always uh, any disturbance at any point in the domain will affect all its neighbors. So this is also a property of the elliptic equation. What about the third one? Is this correct?
No, it's
It is not correct. So initial value problem, it is not initial value problem. We generally have boundary value problems in case of elliptic equations. We define some like the values or the derivatives at the boundaries, and we like solve the problem. Which equation is described by initial value problem? Which kind of equation?
parabolic.
Yes, the parabolic equations are mostly described as initial value. So this statement here is not correct. So 1 and 2 are correct. So I will mark this one correct. All right. Let's move to the next question. Okay. So this is a very straightforward question. What we have to do is basically find out whether this is elliptic or parabolic or hyperbolic. So simply just compare it with the standard equation. So what is the standard equation? This is the standard. So everything other than the second derivatives will go to D. And these second derivatives, second order partial derivatives will stay here, and the coefficients will be a, b, and c. Now, like here, x and y is given. If some other independent variables are given, no problem. And also, you can like an interchange between x and y. Like x is not special; it need not to be the first variable or anything. You can interchange. Still, the nature of equations will remain the same. So let's do like this way only. So what is a here? A is 1 minus r square, right? What is b?
-1.
Zero.
B
0.
is not there. B is not there. So del x del y, this term is not there, right? So b is 0. What about c? C is minus 1, as it said. C is minus. So we need not find the characteristics. It is not asked, so we need not do that. Only thing what we can do is basically basically find this b square minus 4ac. So can you tell me how much this is? Please let me know what is b square minus 4ac.
4 into 1 minus r square.
This. So this is b is 0 and this minus 1 we call it plus. So this is simply 4 into 1 minus. So I have to find whether this is greater than 0 or less than 0 or uh, yeah, greater than 0, less than 0 or equal to 0. So we can see like this, we simply like if r is greater than 1, then this value r square will obviously be greater than 1. So this will become negative. Then b square minus 4ac, this will become negative. If r equal to 1, if r equal to 1, this will become 0. So b square minus 4ac will be 0. And if r is less than 1, then this will be positive. So this equation basically depending on our like the value of this r, this will like either be elliptic or hyperbolic or parabolic. So what is given, r is greater than 1 is given. So uh, what is the if r is greater than 1, whether what is it? Is it elliptic, parabolic, or hyperbolic?
Elliptic.
If r is greater than 1, then this is elliptic. So we will mark that. A very similar type of equation is actually like you may find in like supersonic flows where like this is opposite basically, Mach square minus 1. So if Mach is greater than 1, Mach number, then you will have an hyperbolic equation. If Mach is like less than 1, uh, you would have elliptic equation. So there like this term is basically opposite. In this case, this is elliptic. So, okay, let's go to the next question. So this is our like this is like transport equation. This is a form of transport equation. So this is energy conservation equation. There this temperature is involved. Uh, so in this case, yeah. So there are some conditions which are given, and we have to find out whether this equation is elliptic, hyperbolic, or parabolic. So we first like in this general form, it is like difficult to assess that. So we will first see uh, like what are the conditions given. So if we can simplify this, so it is given that this is one dimension. One dimensional will help us to convert all these nabla operators to simply del del x. So this becomes this. If it is two-dimensional, then we will also have this del del y, three-dimensional del del z as well. But like this simplifies our problem a lot. What else is given? A uniform flow field is there, so this velocity vector, this will be constant. Okay. A very important assumption is given that this thermal diffusivity, this alpha k by rho Cp of this medium is negligibly small, and can be taken 0 for the analysis. So this is a very important like assumption that is given. So let's first work with this, then we will see like the other assumptions as well. So since this form is given, let's do one thing. First thing, let us simply divide the whole equation by rho c. If we divide the whole equation by rho c, we will get this k rho c term, so that we can neglect it. So this nabla operator, this becomes del del x. So this is u infinity t, right? So this is basically constant. We have this k by rho c and del del plus s. So we will it is given that this term is very small. If this term is very small, we can neglect this, and thus simplifies a lot. Why does it simplify our equation? So previously this was a second order equation, right? This was a second order equation. Now it is just a first order. So our solutions can be thus simplified for a like solution of two first order equation. So like dropping this term, if we know that thermal diffusivity will be very less in this particular physical scenario, like for example, like in this case, the other terms might be very like larger, much larger compared to this. Here, thermal diffusivity is not important. Like so, we can remove this, and that will like these kind of assumptions will help us like attain like solution much more quickly. If we incorporate all effects, even those who are whose effects are like not very relevant, then our solutions will like be more complex and it will take more time. So these like simplifications are very necessary to reach our solution uh, like to the required accuracy fast. Okay. What else is given? There is no volumetric heat heat generation. So if there is no volumetric heat generation, which term can I remove?
Yes,
Yes.
yes.
Yes. Yes. So this is our heat generation term. This term we can remove. Okay. Physical properties of the medium can be taken constant. Actually, there is no physical property left as well. Hmm. So we have already assumed rho c to be constant to move it out of the derivative and all. So that is done. Hmm. So we what we are left with is this equation. Now, how can we like find out whether this is a parabolic, elliptic, or a hyperbolic equation? We have so far just seen parabolic, elliptic, or hyperbolic for second order differential equation. However, like we have developed like while seeing for the second order equations, we have developed an idea what it will be like. like how what makes an equation elliptic. It is that like there are no characteristics in the domain, so the information travels at an infinite speed, and like any disturbance that is felt at an felt everywhere in the domain. Hmm. The information is reached everywhere in the domain in an instant, and it is a boundary value problem. So these are the character like properties of an elliptic equation. So whether we are solving a second order or not, these properties, if it applies to the other kind of equations, we will call them elliptic as well. Similarly, like for a hyperbolic equation, we have information traveling at a finite speed. If that is the case, then we will similarly call that particular equation as a hyperbolic equation. Okay, so same thing. So we will also try to like classify this. So for this, what we will do is we will basically convert it to a second order partial derivative, second order partial differential equation. Okay, we'll write the equation. So this is T, this is T, this is X. Okay, so let's do one thing. Let's first differentiate this equation with respect to X. If we differentiate this equation with respect to X, we will have something of this sort. Okay. Again, similarly, let's differentiate this with respect to y. With respect to t, the other variable is t. If we differentiate this with respect to t, we will get this. So this equation has been used to reach here and here. Uh, so what we will do, like for sake of converting this equation, we will let's cancel out the this this term, the mixed derivatives term. You can actually cancel out anything else also if you can, but here you see like both of these equations just have this mixed derivative terms, and like this one has this del square del t square, square, and this has del square del x. Hmm. So these two cannot be cancelled out. So we can only cancel the mixed derivative. So what we will do, we will simply multiply this equation with u infinity in order to cancel with this and subtract. So what does that give us? That gives us so minus infinity square, because we have multiplied another u infinity. This is equal to. Okay. Now we have converted this into a second order PD. So now we will use our like usual process. So please, like for this particular equation, please tell me what is b square minus 4.
For u infinity square.
So So B is 0, and like A, if we take 1, and this is minus U square, so 4 into, and this minus will cancel, this will become 4. So this is greater than 0, right? So if it is greater than 0, what kind of an equation this is?
Hyperbolic.
This is a hyperbolic. So here, this like mm, the there is a speed in which the information will propagate through the medium. So I think someone was trying to join. Uh, yeah. So let me come back to what I was saying. So yes. So this is a hyperbolic equation. So this we expect that the equation that we started with will have the properties of the hyperbolic equation, and it does actually. So let us like try to imagine the physical situation that this equation like portrays. Why I'm asking you to do this, because it is like we just did some maths and found out that this particular equation is a hyperbolic equation, but if we don't know what it signifies, then we will not be able to appreciate it. So here you see, what are the terms that is remaining? This term remains and this term remains, and we have neglected these two terms. So this is heat generation, there is no heat generation, no problem. And what is this? This is the conduction term. So there is no conduction or diffusion of like thermal diffusions. What is there? The convective term is there. So there is a like a velocity which is through which the fluid is the heat of the fluid is being carried, and like that is heating up whatever the water the medium is. So this is the transient term. So this is basically the term which says that at a particular space in the domain, like the temperature of the like material is changed. So that is what this term signifies. So only the convective and this transient term is there. That means like the heat is traveling at a velocity, and that is only like transmitting this kind of behavior. So that's why this is basically limited by the velocity of the fluid, which is u infinity. So this whole process of the like heat transfer which is going on, which is represented by this equation, is limited by the velocity of the fluid. So that's why it is like very like evident that this kind of a equation will be a hyperbolic one, since there is this speed limitation which is there embedded in the equation. Had this convective term been neglected and this diffusion term uh, be prominent, we would have an elliptic equation, an equation which will be elliptic in like space. Because what is the property of thermal diffusion? That is basically it transmits throughout the domain, like a like parabolic, like a elliptic equation. So that is basically the thing to take away when we are like finding out whether some equation is hyperbolic or like elliptic. So here hyperbolic means there is a like velocity attached to this problem. Okay, someone is trying to join.
What does the infinite subscript indicate?
Okay, so I'll tell you. So generally, like let's suppose we solve this kind of equation in fluid mechanics. So what happens? There is a like background, like far field flow. I will try to explain this. So let's suppose some like ball is there, and like near this we are trying to find out some temperature. This wall may have some boundary conditions such as some temperature T0, and like it is basically immersed in a fluid which is flowing around this, and that fluid will have some temperature, hmm, and there will be some heat transfer which is going. Hmm. So if in this case basically near the ball there will be variation in velocity. Hmm. So here the velocity is directed this way, here it will be this way, this will change. uh, and temperature will also change. Temperature also there will be some variation. There are distribution of temperature. Near the ball, the temperature may be near to this T0, but away from the ball, it will be more close to the whatever the temperature the fluid has. So that's what we basically try to indicate very far away from this subject. This ball is the thing we are trying to explore. So very far away from this, we assign that the fluid has a temperature suppose T infinity, velocity suppose u infinity. So these are basically properties at infinity. Hmm. So infinity may not be very like exactly at infinite distance away. It may be basically out of the zone of influence of this particular problem that we are trying to solve. Okay, are you getting my point?
Yes, 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 sir.
Yes. So this is basically velocity at a far away location. Hmm. Or a background velocity. We sometimes like to refer it as a like background velocity as well. Okay. Is there any other question? Please let me know if there is any other question. So now we will like start with the next portion of this course. So we will discuss like variational formulation, weak form, strong form, etc. So let's take a small break. Then we can like resume. Okay. So let's take a break of 5 minutes and then we can resume. Hello. So someone was like asking about assignment deadline. So that you can ask in the like you might have some forum in the your NPTEL like login where you see the course. So you can ask there. I don't have any details regarding the assignment. So let's continue with our session. So uh, yeah. So your like the next portion that we have is uh, the like calculus of variations or variational formulation that we do sometimes to like solve equations. So these are basically like mostly used. This kind of formulations are mostly used in like finite element based methods or boundary element based methods. So in those kind of problems, you will many a times see such variational use of calculus of variation. So here basically the concept is if we have a function and we like integrate this, uh, we have integrate this over a domain. If like let's denote this by I, so we will get a value. Like if we want to minimize this, then we must have a variation. So if we want to minimize this, then we must have delta I this equal to 0. And this is basically the concept. For minimizing, we must have this. And this f is like sometimes referred as a function. So functional basically to distinguish between this f from the like unknown variables which we refer as like functions. For example, if we have like a single independent variable x and we have a dependent variable y, so this y will be called as a like the solution of y will be called as a function. So this functional will consist x, y as well as the derivatives, and like everything will be included there. So let's take up to first derivative, and if there are higher order derivatives, we can also take that. So if we uh, do this delta equal to 0, so delta is like a variation. So uh, so we will do the similar thing for this. This will result in uh, okay. So this will be 0. So I think like I don't need to go through the like derivation again. So this basically, if we simplify this by like doing some integration by parts, what you would arrive at is uh, this. So after doing some like uh, integration by parts, you would arrive at this. And plus there will be some boundary terms. So like if the values of y is provided at the two boundaries, then this will that will become 0. And also like delta x, since this is a our in this is our independent variable, we will also take this as. So what we will basically do is do a integration of by parts for this particular term, and this will lead us to this expression plus boundary terms. So again, boundary terms, why they are 0? They are 0 because we are expected to provide the values, like suppose 0 and L. These are two boundaries. So x is equal to 0 and x is equal to L will have the values for y. This is expected for a boundary value problem. So if that is the case, then our like delta, the variation, that will be 0. Okay. Now if this is like 0 in the like entire domain, and like we have selected it at arbitrary, we would expect for like this kind of a minimization problem over an arbitrary domain, this particular equation to be true. Okay. So this is what is known as Euler Lagrange equation. So you may be like asked to form this kind of equation for a like some random function. So depends on the minimization problem. So if you have like to, for example, one example which is very commonly used is uh, if I have to travel from some point A to point B. So if I have to travel from point A to point B, how what is the shortest path? So this is the minimization problem. So like the whole path, this whole path can be given as integration dl, where each dl, this is equal to this dx square plus dy square root over. So like if we simplify, you this can be simplified to this form ft integration ft, which is this integral that we started with. And we can like simply follow this variational law to calculate this, and we will arrive at Euler-Lagrange equation. Another place for Euler-Lagrange equation is like very commonly used, like you may have also encountered this, is like in case of dynamics. So in case of dynamics we have this Lagrangian, which is like like defined like this, like kinetic energy minus potential energy. So there also what we do is basically like uh, the independent variable is time. Hmm. So we simply minimize this. This is our uh, like problem there. In dynamics, what we do is minimize this integration LDT, and we like come to this equation. You will have the same equation there also, where f is basically L, which is the Lagrangian of the system. Okay. Yeah. So this particular concept of like variational calculus, we will also incorporate in solving our the equations that we are like set to solve here. Uh, like I'm like introducing this topic now, but like if you have any questions regarding whatever I am saying, or like regarding this topic, you may like unmute yourself at any time and ask. There is no problem. Okay. All right. So, let's try to like um, uh, see an example how we can use this variational formulation in solving the type of equations that we do. So we will take a 1D conduction problem. So like conduction equation we have all like already seen this. So this is the energy conservation equation. So if I say conduction problem, which term will be there? This will be there. So if I do steady like conduction, then this will not be there. If there is no like velocity, so when I am saying conduction, generally it is implied that it might be on a solid, or where the velocity is zero. So if there is no like velocity of the material, uh, so we may not use this term. This term will not be required. So conduction like this equal to zero is a conduction equation, or we can have some source. So so let's basically write that equation, and let's keep it in 1D as well to simplify. Yeah. So now since there is only one independent variable x, so no other independent variable is there. It is already like I have assumed it's steady. So I can replace this by this. So this is my like conduction equation. We can have k as a function of x, s as a function of x, but I'm like not bothering to write it down. Okay. So this form of the equation, it is also known as the differential form. Differential, or in short, D form, or strong form. Why strong form? Strong form is basically like in context of what we are going to do right now. So what we are going to do, the next step will be, if this is valid, we will say that, this is also valid. If this is valid, we will say that this is also valid, which is true, right? Because like this whole term is already there, which is equated to 0. So if you simply put equal to is 0 here, we will see, simply have integral of 0, which is will be equal to 0. So there is no problem. Hmm. However, there is a difference between this statement and this statement. What is the difference? So you may speak, no problem. Like someone is trying to speak, I guess. Is someone trying to speak? Priyadarshini, you may unmute and speak. Can someone like say what is the difference between these two, the first and the second line? So we have already established if if the first statement is true, then the second statement will definitely be true. But is the opposite true? If the second statement is true, does that always imply the first statement will always be true? Yeah. So the concept here is basically, so here we have this integral, right? So we are integrating it over the domain. So let's say it is conduction on a rod. So conduction on a rod where there are two ends. One is say, x is equal to 0 and x is equal to L. So I will, this is integrated over x is equal to 0 to L. Now, the first, what does the first statement imply? The first statement implies that this particular equation, this particular differential equation should be valid at each and every point on this bar. Like for each and every point, if I take a differential element, then from all the thermal thermal energy balance, we will get this particular conduction equation. So for each and every point uh, on the rod, this first equation is valid. What about the second equation? This is already talking in an integral sense. So in an integral sense, it is saying that this particular integration will be 0. So this contains this conduction equation. So this particular term is contained, and like any variation in t that might be there. So in the integral sense over this whole domain, it is basically expecting that the conduction equation will hold valid. So this will be 0, and that is the assumption. Is an approximation that we are taking. And due to this approximation, we will see that our problems will simplify, and we will easily be able to solve like this kind of problem. So mm, yeah, so our objective is to put it in a form in such a way that it can be uh, inputted into a computer, or can be solved numerically. So we have to convert like differential equations if we in the raw form, like the analytical solution, that will be very difficult for a numerical engine to perform. However, if you break it down into like some sort of algebraic equations or some expressions, those are much more easier to solve like for a computer. Like numerically, it is very straightforward to solve. So that is our aim basically, to convert this differential equations into more and more simplified versions. So here what we will do, we will like in the next step, we will simplify this term. Okay. Before that, let's do one thing. Instead of writing delta t, let us give it a name. Okay. So this basically represents this. We will represent the variation in the our like main in our dependent variable, which is t in this case. So like v is there and this is there. So we will take this whole term dx k dt dx into v, and we will apply by parts here. So this is, since this is ddx of this whole thing, so this term will be more integrable. So we will take it as our second function, which is more like the more integrable. If we do that, what it will be, we'll have first v uh, dt dx, so this at 0 and L minus integration 0 to L. So here we will have this derivative of this first function dv dx, and we will have here dt this, and we will have this s term as it is. So let's write it in a separate integral 0 to L s. Please let me know if I do some algebraic mistake. Okay. So like we have one term here which we need addressing to, that is the this boundary term. So this is no more in integration. So this is basically at 0 and L what happens. And we already know, like this kind of problem, we would expect some sort of a boundary values. Like some boundary conditions are expected. So here, like depending on what kind of boundary conditions are there are two ways to go about it. One, if suppose t is specified. So let's say at x is equal to 0, t is specified as some t. If t is specified, as we have already seen, the variation in t, this becomes 0. And since v represents the variation in t, what will happen is v will be 0. Okay. So if that is the case, then in that boundary, this is basically 0. What happens if like instead of t, dt dx is specified? If dt dx is specified, suppose dt dx is like uh, some constant, let's say uh, r. So let's say at x is equal to L, that is the case. What will happen then? Then this delta t will not be 0, v will remain, and we will simply have this v, we will put this value k into r, and like go on solving this problem. So what we will do basically, we will like club this to this like this particular integral where v is there. And also notice that like this v is basically not like the v mm, function as it is inside this integral. This is basically v at L. So like that it might remain. Otherwise, like if it is 0, it is if it is not r, this value is 0, then our problem becomes much easier. So you will not have this problem. This then automatically this term will become 0. Okay. So these are basically the two cases scenarios that might arise. One, some t is specified. If t is specified to anything, no matter whether it is 0 or some other value, if T is specified, then V will be 0. So automatically I put this term to be 0. But if DTDS is specified, then it becomes like uh, like we have to know what is the value of DTDS, and likewise we will substitute the values. So for now, let's say the DTDS is 0, or let's say both the ends temperature is specified, whichever. Hmm. So in those cases, basically this term vanishes. So let's for the moment take this as okay. Are you guys with me? Like, is what I'm doing clear to you? Hello, is everyone with me?
Yes.
Okay. If there is any problem, please let me know. If you have any question, please let me know. Yeah. So we have now come to this kind of a function. A dvdx dtdx 0 to L dx. This is equal to 0 to L S d. Okay. So we will again come back to this. This can be represented like a v comma t. So this first term, this is this. The second term, L. I'll come back to this. What why I was able to write this, in which cases I will be able to write this, and like what are the implications. Uh, let's like again just for completion, for sake of completion, let's discuss what are like these essential and natural boundary conditions. So the two type of boundary conditions that we just like discussed. So what they were, like one was the case like I'm using this previous example only, but like in a generic case, you will what you will have a variational variable, and you will have your actual variable, the dependent variable that you are trying to say, or some derivative of it. Here also, like you may have like v dvdx or whatever higher derivatives multiplied with this t or dtdx or any higher derivative. Okay. In essential boundary condition, basically what happens in essential boundary conditions, the coefficient of this variation, whatever this sorry, not the coefficient, this like the variation term. Suppose v is there, hmm, these become 0. Why they become 0? Because some parameter is specified there. So for example, if t is specified, t is t0, something is specified. So what will happen? Delta t will become 0. What about let's say del t del x is specified. Del t del x it might also be specified. Then also it might actually be like uh, uh, essential boundary condition. Then what will happen? Your this will be 0. Del v del x will be 0. Yeah. Hmm. Or not partial derivative, it might be full derivative as well, whatever. So the concept is basically that if your variation term is getting 0, hmm, because like the counterpart of the dependent variable that is specified at that particular point, then it is an essential one. And this is basically essential to be substituted here so that like the rest of the like calculations can be done. Like however you might try to justify the name essential, however you may try to justify the name, no problem. But the like gist of it is this, that what you are actually substituting is the variational value. So v you are substituting in this case. What about in natural boundary condition? You are not substituting v. What you are substituting? You are substituting, for example, like let's suppose in this particular term, if your dtdx is 0 at a particular boundary, then what you substitute dtdx here. Or if your dtdx is specified and you have v as the coefficient, then you will not be able to make it 0, but you have to still write it down. So you will have some v at let's say L, where you have substituted into some like dtdx at x is equal to L, which is like given. So this is a given value, and you have this. So you will have to put something like this in your equation, and like there will be some ways you can accommodate it. When we are actually solving problems with this, which we will do, like we will be studying finite element methods. And there we will be like uh, actually solving these problems and like see how to deal with this kind of situations. So those are basically natural bounding conditions when your dependent variables are to be specified. Okay, so these are basically two types of boundary conditions that you will encounter. Okay, is it clear? Is there any question? Please like feel free to ask. Okay, I will. So uh, yeah, so like just two slides back, you came to this point, right? I will write it down. So we started with this. Hmm. Named it the strong form, and we did some variational calculus, and we arrived at a integral equation where which looks like this. Uh, d dx dt dx, this is equal to integration 0 to L. I have assumed all of them to be essential boundary conditions and like neglected those terms. Okay. Okay. So this form is basically known as weak. Why weak? Because this is like a solution in a weak sense or an integral sense. It is not like not each and every point you are not looking for an exact solution for of the conduction equation. But in an integral sense, you want the conduction equation to be valid. So like you have to remember where this comes from. This comes from basically taking this variation and like putting this across an integral, and over the whole domain you are setting it to 0. So in a weak sense, you are satisfying the conduction equation. That's why it's a weak form. Okay. So now what we are saying is that this particular term, this I will write it as some a p comma b, and this term I will write it as L. This is just a notation, nothing else. So if you substitute t with something else, you will simply put that here. If you substitute v with something else, you will simply put that here. Now, since I have written v here first, I will let me just like change this notation, but you will see it doesn't matter. It does not matter. It is a multiplication anyways, you can see it right now as well. So, v comma t. So let's first explain this LV term because this is something simple. LV is called the linear term. So this is linear. So linear, you know. So linear has this kind of a property. So V1 plus V2, this will be simply L V1 plus L V2, and that is true. You can like simply substitute here v1 plus v2, you will see that this simply breaks into two integrals. So this is the linear term. And also there is another property of linear terms, which is like if you multiply it with something, then it's simply like these things comes out, and you are left with this alpha integral. And here also you can see, like if you multiply it with a constant, it's still inside the integral. This like the constant will come out, and you will get this kind of. So linear is pretty simple. These are the two like properties of a linear. You can simply merge it as one property itself. You have to simply do like this alpha and beta, and you will write here alpha and beta. So then in this way you will not have to write this second property. You can simply merge them into one property. Okay. Now what about this A term? So this is what is a bilinear term. So this has three properties actually. This is a bilinear, symmetric, and positive. The first thing that you notice here is you have two inputs, V and T. So it's a this particular, whatever you call it, function maybe. So this has two inputs basically. So what is the meaning of bilinear? Bilinear basically means both these terms are linear. So if you have this v1 plus v2 comma t, this will become a v1 comma t plus a v2. And if you have this v comma t1 plus t2, this will become a v comma t1 plus a v comma t2. So both these slots, basically this first slot and the second slot, both are linear. So how will it look like if you combine all of them? So if you combine both these, this will basically look like this. Let me write. So A, let's suppose you have alpha v1 plus beta v2, comma, let's say gamma t1 plus delta t2. So this delta is not the variation delta, it is the letter delta. This is equal to, how will I write this? So this is basically, this will break in both V and T. So let me do it one by one. There is a comma here. So let me first break this V. So this will become alpha V1 comma, this portion is there, plus beta A V2 comma, again that portion is there. Okay, I can break this portion as well. So both the times it will be broken. So I can write this as alpha gamma A, this will be V1 comma T1. This is my first term. What is my second term? This will be alpha delta A V1 comma T2. Now I will break this second term. Now I'll break this second term as well. So if I break this second term, I will have beta gamma A V2 comma T1 plus beta delta A V2 comma T2. So basically this means this is a bilinear operator. This is the definition of bilinear. So this is basically linear in both slots. The other two are simpler. What is the next one? It is symmetric. Symmetric basically means b comma t. This is equal to a t comma t. You can keep comparing this with this the term that we have got. So here also you can see, like, if I simply interchange v and t, no problem, because these are multiplied. I can interchange them. And also, like, these are linear in two steps. So ddx, this is the linear operator. And like both of them are like differentiated, like simply first order derivative. So no problem, I can treat them as a linear operator. So both slots are linear. So this is a bilinear operator. So in total, it's a bilinear operator. And yes, so this means this is symmetric. And there is another property which is called positive definite. So positive definite. What is positive definite? Basically, if I have same parameter both sides in the both the slots, then this will be greater than 0, and that also you can see here. So if I simply replace this v with t, then this becomes kd dt dx whole square. So dt dx whole square is positive. So that's it. So these are the properties of this like this weak form. Okay, and we have another form which is like the M form. So I will just treat it and like no, not going to the details here. So this basically follows from the weak form itself. You can see in the lectures it is very clearly mentioned everything. So yeah, so here we basically define a function like this. So this is defined as t plus epsilon t yes minus. So this is a function which is defined. The statement is uh, the minimum value of this function g epsilon at epsilon equal to 0 is half a t comma t. So this is a statement. This is basically simply like similar to your minimization problem. Like the minimization problem, suppose we are trying to solve Lagrange equation, like where we did this, yes, here. Euler Lagrange equation. If you want to solve the Euler Lagrange equation, what is the statement, problem statement for this? Problem statement for this is basically this integration f dx, this is equal to, this is minimum. Hmm. Integration f dx is minimum. If now for that we try to like find out an equation to represent that particular statement, and that equation we what we found is Euler Lagrange equation. So same thing here as well. So this M form is basically a statement. This basically states that the minimum value of g epsilon at epsilon equal to 0 is this. So what we will basically do is basically g dash epsilon at epsilon equal to 0 we will find out. And if we find out like we will find out the yes, we will put this equal to 0. So this will give us the minimum value. So if you put this equal to 0, what is the solution that we find out? We will see that we arrive at nothing but this form, the weak form. So this is basically another form of representing the same problem. So this weak form can be represented by this M form, and both of these are basically representation of the strong form. This strong form. This is the main equation that we are trying to solve. Okay, so let me see how much time we have left. We have time for yeah. So let's do a couple of questions. Okay, regarding this. So here this 1D steady state heat conduction equation is given. There are like few statements which are there. So can you tell me whether statement 1 is correct or not? So V carries the meaning of a small change in temperature T. Is the is the explanations clear to you?
Yes, sir.
Okay, okay. Yeah, can you please like say whether this first statement is correct or not?
I think it's correct.
It's correct. Mhm. Yes, that is true. We just discussed. Basically, here this V variable is a representation of delta T, the variation in T. So V is a representation of delta T. So this is correct. What about the second one? So this is basically like they have tried to represent the weak form, but have they done it correctly?
No, sir.
No,
No. What they have missed? They have missed the negative side, right?
yes.
They have missed the
Negative
negative
side.
side. Yes. So when we did the like integration by parts, basically a negative sign pops up. That's it. So if I put a negative sign here or like change one of these positive signs to negative, it will be correct. So this is not correct. This statement is. What about the third statement? The V form is called the weak form.
Correct.
Hmm. Yes, weak form since it reduces the continuity requirement of the highest order derivative. So yes, this I think I forgot to mention. Like means the advantage that it does is basically you see the like initial strong form which is given by this functional basically. Hmm. So this initial strong form, this is a second order equation, right? Strong form is a second order equation in this case, and our the weak form is a first order equation. So there is a order reduction when we convert it to the weak form, and that like also comes along with the relaxation in continuity and like smoothness requirements of the higher order derivative. And also like you can means if when you convert more strong forms to the weak forms, you will see like if this is a like second order derivative, then your weak form will be first order derivative. If this is for example fourth order derivative, then your weak form will you will see it is second order derivative. You will have to do your integration by parts twice to reach like basically you want to have in this weak form, you want to have the same number of derivative as your this T and V should have same number of derivatives, the same order of derivatives. Hmm. Otherwise, your this A T comma V, this will not be bilinear, right? This will not even if it is bilinear, it will not be symmetric. And those bilinear symmetric, those conditions are basically required to reach the weak form. So basically, your order of uh, differential will half in your weak form. Okay, so this third statement is also correct. So 1 and 3, these are correct. So this C is correct. So let's go to the next question. Here also these two statements are given. So what is the first statement? Essential boundary condition specifies primary variable. Does it? Does it specify the primary variable?
Yes, yes.
So which one is the primary variable in the conduction case example? So we did this. Yes, we use this example, right? So here V or T, which is the uh, sorry, like T or DTT, the primary variable. They are saying like T is the primary variable. So if you provide T, specify T, then your V is basically 0. So this is correct. What about this? Natural boundary condition may specify the primary or secondary variable. Is this correct? So here basically we will like always have this V, this like DTTX, uh, or like in these boundary terms we will always have the variational variable will always have a lower derivative than the this t, because we are always reducing the derivative order of this t. This is the primary variable. This the dependent variable. Uh, this order we are reducing. Hmm. So whenever for the natural boundary condition, what we like said is basically this mm, this higher order derivative, this dtdx. This if it has some value specified at the boundary, then this becomes a natural boundary condition. Then you will have to deal with whatever the boundary the value has been given. Hmm. So for a higher order derivative, if the value is like provided, then it becomes a natural boundary condition. Otherwise, if your like lower order derivatives values are provided, then it stays essential boundary condition. Then that's what this question is trying to indicate. In this like primary and secondary variables, like we also treat this dtds as a variable in your in the function. So if your like the higher order derivative value is specified, then only it is a natural order natural boundary condition. If primary variable is specified, then it will not be a natural boundary condition. Then your v will be 0, and you can like call it an essential boundary condition. So this second statement is false. So primary variable, if it is specified, then it becomes essential boundary condition only, not natural boundary condition. Okay. So here this is this option will be. So this is the M form basically. So here this is a basically minimization problem that we just discussed right now. Uh, so here there the question is not about the M form. The question is about A. What A must be? What are the properties of A? So we just discussed the properties of A. What are
C.
the yes, yes, bilinear, symmetric, and positive. Bilinear again. What is bilinear? Bilinear is basically this like both these slots. Both the slots are linear. What is symmetric? Symmetric is very straightforward. This is equal to v comma k. And what about positive definite? Positive definite is if both these are same same variable, then this is a positive quantity. Okay. When you convert like M form to D form or a weak form, a V form, or V form to M form, then you will need these conditions like to arrive at these forms. So these are given in the lectures itself, so I'm not like deriving them in the live session. Let's do this question. Keep it the last question. So we have to select which are essential boundary conditions, essential or natural boundary conditions. So what is the order of the derivatives here in the strong form? So this is the strong form, right? This is my strong form. What is the order of this equation? Which order?
Third one.
Sorry, I couldn't hear. Can you speak again? Your sound did not reach me. Can you speak again? Who's speaking? Hello. Yeah, what is the order of this equation? This is a sixth order equation, right? There is like order 3 here, and again order 3 here, which is operating on this. So if it is operating on this, this will be sixth order ODE. This is an ODE because there is no partial term here, only one independent variable. Okay. Yeah. So the boundary conditions are given likewise. Six boundary conditions will be required, and it is given. We have to select the which one of these are true. So we have already discussed like if like y is provided, dy dx is provided, or in this case d2y dx2 is also provided, then these will be essential boundary conditions. Why? Because when we are converting this into the weak form, we will like not encounter these. Hmm. Like we will be only reducing this the power of the order of derivative for the y, and we will reduce it till like the variational variable, let's suppose b, reaches the same order of derivative as y, and that will happen in the third order derivative. So the weak form will be a third order derivative. Hmm. So till that, these variables, these conditions, these will be essential boundary conditions, and the rest, the higher order terms, those will be natural boundary conditions. So let's select. So here these are natural boundary conditions. So this is not true. So this is these two are, if these two are specified, then these are essential boundary conditions. This is true. That's what we discussed. This is third order derivative, already a higher order derivative term. This is fourth order derivative term. So if these are specified, then this will be natural boundary condition, not essential. This statement is false. Again, here we see fourth order derivative and fifth order derivatives. These are also like natural boundary conditions, not essential boundary conditions. So this is also false. So option B is the correct one. Okay. So we will discuss like some other things are also there to discuss from like week 2. We will do that in the like next class. Uh, Please like means go through the contents very carefully. Like you will be requiring all of this in your assessment tests, and like if there is any like question week by week, please like uh, keep those questions ready so that we can like discuss the questions in this live sessions. Okay, whatever I am discussing till whatever point I have discussed in this class, if you have any questions, please like accumulate that questions in one place so that you can like ask in the next live session. We will I will be happy to discuss that. Okay. So, is there any questions right now? Okay. Uh, I'll close the session then. Thank you for joining. We'll meet again on like next Tuesday.
Thank you, sir. Thank you.
Thanks.